recording is in progress, and now I can share my slides. Okay, so I hope that you guys are able to see my slides. Let me quickly pull up chat box. Okay, let's get started. So what are we doing today? We are going to continue our discussion on eigenvalues and eigenvectors. So in the last class, we looked at the roots of the characteristic polynomial, and the examples that we looked at in the last class had all real roots for the characteristic polynomial, which means that you had real eigenvalues. But what if the characteristic polynomial is such that the roots are complex? Then how do you deal with eigenvalues or eigenvectors that correspond to those complex eigenvalues? This lecture is going to be about that. How do you deal with complex eigenvalues and eigenvectors? So we'll take a look at do the eigenvalues that are complex, do they come in pairs, and are there some properties about complex eigenvectors or not? So those are the kind of things that we are going to be looking at in section 4.6 of the text. So it's not a pretty long lecture today. It's going to be pretty short. So let's see if we can get through it rather quickly today. So complex roots of characteristic polynomial, right? So you were setting up the characteristic polynomial by using this. So first you started with, say, characteristic polynomial for a given matrix A was set up by first evaluating A minus Ti, some T, that's your scalar, I is your identity matrix with the same size as A, and you find the determinant of that, then that would give you your characteristic polynomial in T or lambda, whichever one you want to use. Now, if the size of the matrix A is n by n, it is a square matrix of size 4 by 4 or 5 by 5, n by n matrix, then the number of roots that you can have at maximum, the polynomial is going to be of degree n, right? So if you have a 4 by 4 matrix A, then your polynomial that you are going to get for the characteristic polynomial is going to have a degree of 4 in n. And every root of that characteristic polynomial is going to be your eigenvalue of A. It could be real, it could be complex. But we know that at most you can have n distinct eigenvalues. So if we quickly sketch something, say for example, you're trying to sketch, say we try to sketch on the x-axis, say we have t, on the y-axis, say we are sketching the characteristic polynomial p of t. Now, if this guy has some shape like that, then you know that these are going to be your two real eigenvalues, right? So these are going to be your two real eigenvalues. Right? P of t going to 0. So the solutions of that over here are real. However, if you have the characteristic polynomial, say the second, some other characteristic polynomial like this, which never crosses the x-axis, then it is not going to have real eigenvalues, but it is a polynomial of a higher degree. So it is going to have its roots to be complex, which means that for this guy, it is going to be complex eigenvalues. And the eigenvectors that will correspond to complex eigenvalues will also be complex. And we'll take a look at that. So for the red guy, your P of t was crossing the x-axis. So there you got two real eigenvalues there. Let's see. Let's go back and take a look. So some of the eigenvalues may be complex. We just saw an example of that orange sketch there. And so what we are going to do today is we are going to work through some of the issues that this could cause in determining eigenvalues and, more importantly, eigenvectors that correspond to that. So we drew a sketch there. That's fine. All right. This is an example that we saw in the last class, but we didn't actually go ahead with it with this example. We didn't go quite far. We didn't find the eigenvectors for the complex eigenvalues. So let's try to do that over here. You're given a 2 by 2 square matrix A. So it's a simple case, 2 by 2. You're trying to find the eigenvalues and eigenvectors. So the first step over here would be what? You would set up the characteristic polynomial. So if you're given A, then you're trying to go for A minus Ti. Well, A is 2 by 2, so you're using the identity matrix of size 2. And then if you find the determinant of this guy, that would give you your characteristic polynomial, P of T. And if you see this, the only elements in A that would get affected because of this subtraction are the elements in the diagonal of A, in the principal diagonal of A, because only there the identity is going to be a 1. Everything else is a 0. So if you take this guy and try to apply our characteristic polynomial discussion there, what do you have? 0 minus t gives you minus t, 0 minus t gives you minus t. The other two elements remain as is, and you're trying to find the determinant of this 2 by 2 matrix there. You get t squared plus 1. Now t squared plus 1, if you try to sketch it, on the x-axis you have, say, t, on you have t there, you have p of t there, and you have, in this case, t squared plus 1, right? So t squared plus 1 is going to be doing that, and you can see that you need two roots for this, right? T squared plus 1. So it's a quadratic in t. You know that there are two roots, but it is not crossing the x-axis, which means that both those roots will be complex. And in fact, they will be complex conjugates of each other. Let's take a look here. So eigenvalues for this. So t squared plus 1, set it to 0, find the values of t that will satisfy that. You will see that the complex, the eigenvalues will be complex, plus and minus I. So you know that they are complex conjugates of each other, where I denotes square root of minus 1. We all know that. Now that you have got the two eigenvalues, you can use those two eigenvalues to find the corresponding eigenvectors. So the first case over here, set lambda to be I. The first case, the augmented matrix is going to be A minus lambda I. So small I is your square root of minus 1. And then capital I is your identity matrix, in this case of size 2 by 2. So you're looking for the null space of A minus I cap I. So the augmented matrix over here is going to be A minus lambda I x equal to the 0 vector. You have A minus lambda I to be this. So over here we did minus ti. Over here we are doing minus I. So all the t's will be replaced by i's, and you get that. And because you are setting up an augmented matrix, all the way to the right you have the 0 column there. Now from here you can apply use row reductions to find the solutions to this, because we want to find the null space of A minus II, right, for the eigenvector. What we want to find is null space of A minus II. And we are doing that by forming the augmented matrix, doing row reductions, and then going and discussing the solution set. So from here, our row reductions now are not going to involve things that are real. Now they are going to involve things that are complex. So for example, the first step over here is actually taking row 1 and multiplying it with I, right? So if I take row 1 and multiply it with the complex number I, what do I get? Minus I times I get a 1. 1 times I get an I. 0 times that is the same. And then the second row, I have not changed that at all, right? So I've taken the first row, multiplied it with an I, I've got that. Next, from here, I can see that the first row and the second row are linearly dependent. One is the negative of the other. So I can do row 2 plus row 1, right? Like I can simply do row 2 plus row 1 over here. And what I get is 0, 0, 0 for the second row. And I get 1, I, and 0 for the first row. From here, I can read out the solutions now. So I can use this and say, all right, if I use the first row here, I know that x1 plus I x2 equals 0. And x1 is my leading variable in this row reduced echelon form matrix. So I let x2 to be a t, some arbitrary value, and then that implies that x1 is going to be negative, negative it, right? Which for the solution set x, which is going to be x1 and x2, that I can say that this is going to be t, not t, minus it and t. And if I pull out that t up front, what do I get? I get t minus I and 1. So that's what I'm writing over here. So let x2, your remaining variable, to be some arbitrary value t. Then you get x1 to be negative it. And then you can write the eigenvector. This should be bold. This should be bold. So I'll just put an underline here. So eigenvector x here is going to be t, some arbitrary value multiplied by negative I and 1. So all the vectors that are going to satisfy this, for example, negative 2i2, that will satisfy, negative 3i3, that will satisfy that. So all those vectors are going to be eigenvectors, which means we have found the null space of a minus small I capital I for the eigenvalue lambda equals I. Now you can obviously check this, right? Like this x, if this is an eigenvector, then it has to satisfy ax equals lambda x. If that is the x, that's the eigenvector, then it will satisfy that. Let's check it. Let's try to evaluate ax. A we know from earlier, x we just found out, and over here we are checking it for the value of t equals 1. Multiply the two matrices, you will see that it evaluates to 1 and I, which is the same thing as saying I times x, right? So what you have is ax equals lambda x. Let me just highlight that. Ax, you got that to be lambda right there, and the same x that you had earlier. So this satisfies, which means that your minus I and 1 is in fact the eigenvector that corresponds to lambda equals 1, lambda equals I. Now, before I even try to go ahead and find out for lambda equals minus I, because that's the next eigen vector that is left, this is a property that exists between complex eigenvalues and complex eigenvectors, which is complex eigenvalues will occur in pairs. They will be complex conjugate pairs. And that also applies for eigenvectors. So right away, I know what my answer is going to be for the second case here when I consider lambda equals negative I. But let me just try that, point that out to you guys over here, which is if I consider lambda equals negative I for the second case here, I would get my eigenvector to be t. Instead of minus I, I'll get a plus I, and 1 is a real number, so that doesn't change. So I'm going to expect that when I go for the second case here, I'm going to get that as my answer. But in any case, I will just go ahead and lay out all the details here. So the only thing that is left for me is lambda equals negative I, the second eigenvalue. I'm going to try to find its corresponding eigenvectors. I've set up the similar augmented matrix, in this case a plus small I capital I x equals 0. So I'm trying to find the null space of a plus I set up the augmented matrix, then I do some row manipulations. What are the row manipulations I'm doing here? I'm multiplying by negative, right? So I'm over here, I'm doing negative I row 1, and in the second case, I'm just doing row 2 plus row 1. And if I do those row manipulations, I get the second row goes away. The first row will give me my solution set. I can pick x2 my remaining variable to be t. Using that, I can find out my leading variable x1. I will see that it'll be it, and then I know that this will be giving me the eigenvector. That's what's supposed to be bold there. Eigenvector is t times I1. And again, I can use the similar check. Ax equals lambda x. Does this x satisfy that for this particular lambda or not? So I set up Ax. I know A from my original matrix. I have my eigenvector that I'm checking for. This will equal 1 minus I, which I can write that as negative I times x. So this will satisfy, which means that my ti1 is going to be any vector that is in the form of t times I1, right? So 5i5, 10i10, and so on. All of these are going to be eigenvectors for lambda equals negative I to be the eigenvalue. And you see, I had reached that same conclusion earlier itself, right? Like this I had seen that already. So this sort of validates that statement, which we are going to later on prove, that eigenvalues and eigenvectors will appear in complex conjugate pairs. All right, let's move on here. Now, complex conjugate. So if you are not familiar with what a complex conjugate is, it is simply negating the imaginary part of the complex number. So if a complex number z has this particular form, a plus ib, right? So in the complex plane, you can take a look at this. So you can, if I add a slide here, say this is my complex plane of complex numbers, then I can use real part on the x-axis and I can sketch imaginary part on the y-axis, and any point in the plane, let's say I have a point here and I'm using z for this. Z is my complex number and it has a real part of a and ib. I is square root of -1, b is the imaginary part of that z. So if I project that point onto my real and imaginary axes, I will see that, let's see here, line, this is going to be, over here, real part is a and imaginary part is b. And if that is my complex number z, the complex conjugate is going to be on the other side of the real line. So my complex conjugate, let me put that in red, is going to be over here. Hopefully it'll match the scale right there. So in this case, the real part doesn't change, but my imaginary part changes the sign. So this one is going to be z conjugate. Sometimes it is represented with a bar over it, or sometimes by an asterisk, doesn't matter. That is representing the conjugate of z, which is going to be a minus ib. The real part is the same, a. The imaginary part over here is minus b. Right. So this discussion is essentially showing you that, yeah, if you have eigenvalues, you're going to see pairs of complex conjugate eigenvalues. So all you're doing here is the complex conjugate of z is simply take the imaginary part and flip the sign. So a plus ib, complex conjugate is a minus ib. Now notice what happens to the product of the z and complex conjugate of z. So if you try to evaluate the product of z and z complex conjugate, z is this guy, z conjugate is this guy, you expand it up, you will see that you get a squared plus b squared. Right? A squared plus b squared being the distance from the origin squared, right? So it's the magnitude of z squared, which is going to be the same thing here and here. The length is going to be the same. So let me just point that out here. So this guy from here to here, the length is going to be magnitude of z there, and the same thing applies on this case. If I draw a line there to that point, it still has the same magnitude of z, right? Which is going to be what? Which is going to be square root of a squared plus b squared, and the same thing applies on the other side. But when you do just z times z conjugate, you get the square of that value. So you get a squared plus b squared. Right? So you get a squared plus b squared. So which is the square of the magnitude of z. But how is this important to us? It is important because eigenvalues and eigenvectors are going to have complex conjugate pairs. But also, when you're trying to find the eigenvectors for a corresponding eigenvalue, you're going to have to do some Gauss elimination. And you're going to have to deal with Gauss elimination for numbers in your matrix that are complex. So a strategy over here is going to be, you don't want to divide a row by a number. Instead, you want to multiply by the complex conjugate of the number. If you see that it is complex, then you multiply it with the complex conjugate of that number. And then later you can divide by the square of its magnitude to make it a 1. Let's just try to see what that means. So suppose you have some complex number z that appears in your augmented matrix and you're trying to do some row reductions there. Now, instead of dividing by z, what you can do is you can multiply by z conjugate, multiply by z conjugate. Let me just be consistent here, z conjugate. So when you multiply by z conjugate, what do you get? You get z entry will become z conjugate, which means you get a squared plus b squared. And now when you divide it by a squared plus b squared, the square of the magnitude, right? Square of the magnitude, what do you get? You get a 1, right? So suppose there was a particular leading variable, you wanted to force it to be a 1, then you can use this strategy to force it to be a 1, right? So all you have to do is take that complex number, multiply it by the conjugate, and then divide it by the square of the magnitude of that particular complex number. You get a 1. So you can turn a complex number, complex entry in a matrix into a 1 by using this strategy. All right, let's move on here. We talked about this. All right. Now, let's try to do some examples. Here we have a 3 by 3 case. So we are trying to find eigenvectors of this particular square matrix. It is a 3 by 3 square matrix. Our, starting is going to be the same. You go for a minus ti, find the determinant, set it to 0. You've got a characteristic polynomial, try to find the roots. And for each of those roots, find the corresponding eigenvectors. So all of those things have been done over here. So the first step being a minus ti. So you're doing a minus t there, and a minus t there. Then you find the determinant. Now in this case, it is convenient to take this guy and expand it on the basis of that, right? So you can do the cofactor expansion using any row or any column. But because you know that the third row here and the third column here has 2 zeros, all you would need to do to find the determinant is expand using the third row or the third column. They both are the same thing over here. So I can say it's going to be 1 minus t, right, multiplied by the determinant of whatever remains. So in this case, what will remain is this. So I have 2 minus t, 1, negative 5, and negative t. Right? So that's your characteristic polynomial, p of t equals. And if you simplify this down, you get this. 1 minus t times a quadratic in t. So if you even expand it out even further, what you have is a polynomial of degree 3, which is consistent with our discussion. 3 by 3 matrix, you got a polynomial of degree 3. What are the roots? Well, if you would have to factorize the polynomial. And if you factor it out and look at the roots, you get a real root from here, right? So a real root from here, 1, that's your eigenvalue. And because of this guy, you can solve the quadratic equation, look at the roots, you will see that you get 2 complex conjugate roots, 1 plus or minus 2i. So those will be the values of t that will make that characteristic polynomial go to 0. So now you have 3 eigenvalues. For each of those 3 eigenvalues, we are going to look at what the eigenvectors are using the same strategy, right? So lambda equals 1, that should be straightforward. We are looking at the null space of a minus I. So a minus I, you set up the augmented matrix. A minus I is written over here. So first we set up the augmented matrix. Let me just write that up. Set up augmented matrix. The matrix is going to be what? It is going to be A minus lambda is 1, I, X should equal 0, right? That's your augmented matrix. A minus I is this guy there. So when you're trying to set up the augmented matrix, you would add another column of zeros there. And then you would try to go for row reductions to find the solution set, right? The null space of A minus I. And you guys have done that many times. So I'm not going to do that again over here. But if you do that, you will see that your solution set, the null space of A minus cap I, will be any vector that has this particular form. The first element is 0, the second element is 0, and the third element is any arbitrary value, t. So that is going to be your eigenvector for lambda equals 1 as your real eigenvalue. And you can again check it. Ax equal lambda x. Lambda is 1. So Ax equal x. Does it satisfy it or not? What A are you going to use? You are going to use A is this, right? Your original matrix. And then the x that you will choose for some t, right? You can pick t to be a 1 and see if this satisfies or not. And it will. So, you know, the discussion for the straightforward real eigenvalue is very similar to the ones that you have seen before. But because of complex entities in the augmented matrix, the discussion for complex eigenvector evaluation for complex eigenvalues is slightly different. So let's take a look at that. So next, what we are left with is this. We are left with eigenvalues that are complex conjugates of each other. For the real one, we already did that. So we are left with 1 plus or minus 2i. We are looking at the same 3 by 3 matrix here, A. We are left with finding the two more sets of eigenvectors. So we'll consider 1 plus 2i first. So eigenvalue is 1 plus 2i. We will set up the augmented matrix A minus lambda I x equals 0. So in this case, lambda is 1 plus 2i, small I. So we've got the augmented matrix over here. Once you have got this augmented matrix, notice how you're making this into a 1. You have to multiply with the complex conjugate of that number. And that's exactly what you're doing here. You see 1 minus 2i, you're multiplying that by 1 plus 2i for the row 1, you get a real value. This guy goes to a complex value, but then you can force that to be a 0 later on if necessary. But you wanted a leading one there, and you can get a leading one there if you divide row 1 by 5, which you're doing over here in the second step. All the other row operations are also listed over here. Eventually, what you get is a matrix that has leading ones, but it also has a complex entity over here. So from this row reduced echelon form, you can look at the solution. So what is the solution going to be? Well, if you look at the second row here, the second row is simple, right? So second row will tell you that x3 is a 0. And the first row will tell you that x1 plus 1/5 of 1 plus 2i times x2 equals a 0. And if you pick x2 to be some t, right? If you pick x2 to be some t, then you can find out x1. You can say x1 is going to be negative 1 over 5 times 1 plus 2i t, right? So you have got the solution. What is that? The solution over here is the last element has to be a 0. The second element, the middle element has to be some arbitrary value t, and the first element has to be that t, that same t multiplied by negative 1 over 5 times 1 plus 2i. And that's how we are writing the solution here. So x, the eigenvector over here is going to be some arbitrary value t multiplied by negative 1 over 2i. So you see, you can multiply all of these guys by 5, right? Like you can multiply this by 5, by 5, by 5 without any change, without any problem, because t is some scalar. So if you do that, you can write it without that 1 over 5 factor in the eigenvector, which is optional, of course. So for the first element, you got negative 1, negative times 1 plus 2i, so negative 1, negative 2i. For the second element, you've got a 5 times t, and for the last element, you've got a 0. So those are your eigenvectors. And right away, I also know what my eigenvectors are going to be for when I consider 1 minus 2i, the second complex eigenvalue. It's going to be just the first element. The other two elements are real, so I don't even have to manipulate that. Those are going to remain as is. Only the first element is going to become the complex conjugate of the eigenvector over here. So instead of getting minus 1 minus 2i, you will get minus 1 plus 2i. That's it. But in any case, I'm going to just look at all the steps over here. So the last step over here, the third eigenvalue is 1 minus 2i. Let's find the eigenvectors for that. Lambda is 1 minus 2i. So you're setting up the augmented matrix A minus lambda I equals 0. I is 1. This is the typo there. So because you're using A minus 2i here, this should be A minus 2i. X equals 0. You've got the first the augmented matrix. Now we are going to start doing row manipulations. The first step is multiply by the complex conjugate of this particular number to get a real value. You did that. Now you're trying to manipulate it in such a way that you get row reduced echelon form. So the steps over here are given. Eventually you will get a row reduced echelon form for the augmented matrix. Using the similar steps as before, you are going to take a look at the solution. The solution, the eigenvectors are going to be of this particular form. T times negative 1 plus 2i, 5 and 0. And just as we said, they are complex conjugate of the previous eigenvector. So if eigenvalues are real, then you cannot really do anything about that. You have to go through the entire process of finding out the eigenvectors. However, if eigenvalues are complex, then they will appear in the complex conjugate forms, and you only need to evaluate the eigenvectors for one of those complex conjugate eigenvalues. The other one will be the complex conjugate pair, so you don't have to go through the steps for the second eigenvector. Now let me just say, if suppose you have 5 eigenvalues, right? So suppose you had A as a 5 by 5 matrix. If you have A to be a 5 by 5 matrix, then the characteristic polynomial will be of degree 5, which means that it will have 5 roots, right? So when you have 5 roots, a few possibilities could happen. With 5 roots, you can have all 5 to be real, or you could have one real value and 2 pairs of complex conjugate eigenvalues, or you could have 3 real values and then 1 pair of complex conjugate eigenvalues, right? So these are the 3 possibilities over there if you have an order 5. All right, let's move on here. Right, so let's check, right? So we evaluated eigenvectors for all the cases. Let us just check whether the eigenvectors that we obtained do satisfy our ax equal lambda x equation. So we already did that for lambda equal 1, the real value. Let's check it for the 2 complex eigenvalues. So lambda equals 1 plus 2i. That particular eigenvalue gave us this particular eigenvector. A is the same for both cases, so A is being referenced over here. So we are trying to check whether ax equals lambda x or not. Lambda is over here. X is over here. A was the given matrix. So try to evaluate ax. You will see that it'll simplify down to this particular vector: 3 minus 4i, 5 plus 10i, 0. And because you cannot straight away try to match this with lambda x, you can do evaluation of lambda x separately. So let's try to evaluate lambda x separately. Lambda is 1 plus 2i. X is the same x as before. If you multiply these two, which is essentially a scalar multiplication here, what you will see is you will get 3 minus 4i, 5 plus 10i, 0, exactly matching ax. So you know that this x with this particular lambda satisfied ax equal lambda x. Next, do the same thing for 1 minus 2i. 1 minus 2i, a different eigenvector. In fact, the complex conjugate eigenvector for the previous case. A is the same. Evaluate ax, evaluate lambda x, check whether they are same or not, and it will turn out to be exactly the same. So this proves that, in fact, the eigenvectors appeared in complex conjugate pairs here. We had one real eigenvalue, which gave us one real eigenvector. But for the two complex conjugate pair of eigenvalues, we got two complex conjugate pair of eigenvectors. When I say complex conjugate pair of eigenvectors, what I mean is each element in the vector will become complex conjugate of the original one, right? So if it is real, then it will not change. So if you see this, 5 and 0 remained as is, only the first one, which was a complex number, became for one, this guy, 1 minus 1 plus 2i, only that guy changed, right? Minus 1 minus 2i earlier. All right, let's move on here to the next slide. So this is essentially capturing that particular observation, complex conjugate pairs. So in the example, the two complex eigenvalues were 1 plus 2i and 1 minus 2i. In fact, in our 2 by 2 example that we saw earlier, 2 by 2 example, what did we have? We had eigenvalues, eigenvalues were plus or minus I. Again, complex conjugate, right? So those complex conjugate eigenvalues corresponded to these eigenvectors. You had some arbitrary t multiplied by that vector for the first case, and some arbitrary value t multiplied by this eigenvector for the second case. And again, these are also complex conjugates of each other. Real values don't change. However, complex values are appearing in complex conjugate pairs. Now, this holds in general. So all you have to do is find the first complex conjugate vector x. The second one is simply going to be the complex conjugate vector x bar or x conjugate, which is obtained by simply taking the complex conjugate of each element. All you have to do is negate the imaginary part. And this is always going to be true. Next, we have a theorem here relating eigenvalue and eigenvector for complex conjugate pairs. The theorem is, if A is a square matrix and if it has an eigenvalue lambda that corresponds to eigenvector x, then the complex conjugate lambda bar, right, the complex conjugate eigenvalue is also an eigenvalue of A, and its corresponding eigenvector is going to be the conjugate vector x bar. So if you have lambda and x as eigenvalue and eigenvector for a particular matrix A, and if lambda happens to be complex, then lambda bar is also going to be an eigenvector of A, eigenvalue of A, with the corresponding eigenvector to be x conjugate. Let's try to prove this, and we'll try to prove this based on one particular fact, one particular property of complex numbers, which I will lay out over here. So I will assume that we have two complex numbers. Let A plus IB and C plus ID, right? These are two complex numbers. B then the conjugate of their product equals the product of their conjugates. And we can try to prove this very quickly. Let's consider two columns here. Just make two columns. And then on the first side, I will evaluate, say, A plus IB multiplied by C plus ID, the whole thing conjugated. And on the left side, on the right side, sorry, let us evaluate A plus IB conjugate multiplied by C plus ID conjugate. Let us try to see if these guys are going to equal or not, because the proof is going to rely on this. So let's take a look. Over here, what do we have? We have A plus IB. So let's try to do the multiplication first. So we have equals, we have AC plus I squared BD plus IBC plus IAD. And the whole thing needs to be complex conjugate. Now when I squared is -1, so we can write that as all right, so what is the real part going to be? Real part is going to be AC minus BD plus, factor the I term here, we get BC plus AD, and then we still need to do the complex conjugate. Now the next step is going to be just applying the complex conjugate. Real part remains as is, and the imaginary part is going to get a sign reversal here. So when you satisfy the simplify the left hand side, you got that. Now let's try to take a look at what happens to the right hand side. I can directly apply the complex conjugate for each of these numbers first. So A plus IB becomes A minus IB multiplied by C minus ID. Let's try to multiply it out. AC minus IAD minus IBC plus I squared BD. AC minus BD minus I AD plus BC, and they both match, right? So if when they both match, you know that conjugate of their products, right? Conjugate of their products, which is this guy, equals product of their conjugates. We are going to use this particular property to help us prove this. So let's go back and take a look. So that's what the proof is exploiting. So let's try to use this. So we are given what? We are given that lambda is an eigenvalue of A with the eigenvector x. So the moment you know that, you can write AX equal lambda x, right? You can write that based on the given assumption. Now let's try to evaluate lambda x complex conjugate of that. Well, we just now saw that based on the property, lambda x, the conjugate of the products is going to be the product of the conjugates. So you have lambda conjugate here, x conjugate here. So based on the previous discussion, the next slide, right? This slide right here, we can write this. The other thing that we are going to exploit is this, which is AX complex conjugate is going to equal what? This guy will equal A conjugate multiplied by X conjugate. However, A conjugate will equal this because A is real. So if A is real, A complex conjugate and A are real. So we can say AX conjugate will be AX conjugate. Next, consider AX conjugate, right? So we are trying to evaluate whether X conjugate is an eigenvector or not. So AX conjugate is what? We can write that as, using the previous statement, we can write for this, we can write AX conjugate. We are writing that. AX conjugate, earlier we said lambda and x are complex value and eigenvalue and eigenvector for A. So for AX, I can substitute lambda x. I'm doing that right here. For AX, I'm substituting lambda x. The conjugate operator remains as is. Next, use this property here. All right, let me just mark and point. Mark and point. And mark and point. So for the last one, you have lambda x conjugate will be the product of the conjugates, which is lambda x x conjugate, lambda conjugate and x conjugate. Now if you take a look, see, you take a look at this and this. If you compare those two, you see ax equals lambda x. In this case, x is x conjugate, lambda is lambda conjugate. So lambda conjugate is an eigenvalue of A whose corresponding eigenvector is simply x conjugate. So if this is true, then this is also true. So x conjugate is an eigenvector of A with lambda eigenvalue lambda conjugate. So I hope that was helpful. Let's move on to symmetric matrices. So for symmetric matrices, your eigenvalues will be real. And of course, if I say eigenvalues are going to be real, then eigenvectors are going to be real. So that's the theorem, and we'll prove it. So if you have a symmetric matrix, you know that A should equal A transpose, right? So if you switch all the rows and the columns, then you should get the same matrix. For example, if you consider A to be, say, 1, 2, 3, 4, 5, 6, then, you know, if A has to be symmetric, then I need this to be 2, 3, and this to be, let's see, 5, right? So if I switch the rows and the columns, I get back the same thing. So that's a symmetric matrix. Now, for symmetric matrices, all the eigenvalues are going to be real. That's the theorem. And if all the eigenvalues are real, then you know the eigenvectors are going to be real, and they are going to form a basis for R to the n. All real eigenvectors. Now, for the proof, let me just prove it on the next slide here. What I'll consider is x. I'm going to consider x my eigenvector conjugate transpose multiplied by matrix A multiplied by vector x. What is this going to equal? Well, that is going to equal x conjugate transpose remains as is, because I know that lambda and x are eigenvector and eigenvalue for A. I can replace ax with lambda x. Now I'm not writing x with a bold line or underscore. You know with context that x is referring to that eigenvector and lambda is for the eigenvalue, right? So this is since x is eigenvector with lambda as eigenvalue. Next, what is this going to equal? This will equal lambda is a scalar. I can pull it up front. And what I'm left with is x conjugate transpose multiplied by x, right? So let me just leave that result for now and consider some other product. So let me just draw a line here. And next, I will consider something else, which is x conjugate transpose ax. And I will write it slightly differently, which is x conjugate transpose multiplied by A multiplied by x transpose. Now, the reason why this is true, this will be true, is because the left-hand side is simply going to be a scalar. So let's try to take a look at this. If you look at the size of each of these vectors or matrices, what do you have? For x, what was x? X was n by 1, right? Which means that x conjugate transpose is going to be 1 by n. And A was simply n by n. Now when you do, and you know nicely these are matching, which means that you can actually do the matrix multiplication. But when you do the matrix multiplication, your overall result is simply going to be a scalar. The answer is going to be scalar, 1 by 1 scalar. So if it is going to be a scalar, there's nothing to switch, right? There's only one row, one column, which means that when you switch it, you get back the same thing. So because of that, you can write that this particular product here is going to be the same thing as that same thing transposed because it's a scalar. All right, so that's that. Next, this is going to equal x transpose A transpose x conjugate. How is that? Product of the matrices transposed will be transpose of each of them in the reverse order, right? So we did x transpose first, A transpose next, x conjugate transpose again, you get back x conjugate. And because A is symmetric, because A is symmetric, you can actually just erase this off. A transpose equals A, right? So this will be this. The reason here is A is symmetric. Next, for this AX conjugate, I can write that as what? X transpose as is. AX conjugate is going to be lambda conjugate X conjugate. Why? Because we have already seen that eigenvalues and eigenvectors will appear in complex conjugate pairs. So for AX, AX conjugate, I'm writing lambda conjugate X conjugate. The reason over here, since X conjugate is also an eigenvector with lambda conjugate as eigenvalue. Next, lambda conjugate is a scalar. I can pull it up front. I'm left with what? I'm left with X transpose X conjugate. And X transpose X conjugate is the same thing as writing lambda conjugate X conjugate transpose with X conjugate. And the reason is, you see, what is this? This is a dot product between all the elements in X with all the elements in X conjugate. It should be the same thing as doing a dot product between all the elements in X conjugate with with X, right? Because you just need to conjugate it once, but this transpose this and this transpose this, they are both dot products of two vectors, X and X conjugate. They're both of them are the same, so I can replace with doing that. Next, now I will try to compare. Zoom out, take a look. This guy, which we considered in both cases, gave us this and this. So that means that those two should be equal, right? So now I can say, so lambda X conjugate transpose X should equal lambda conjugate X complex transpose and X, right? Next, what I can use is, what about X complex conjugate with X? So take a look at X conjugate transpose with X. That is simply going to be the magnitude of X squared, right? Dot product of all the elements in X, the other vector is conjugate of X. So when you're multiplying each of them, you are evaluating A squared plus B squared, right? Like if each element in A is complex, A plus IB, the other one will be A minus IB. And when you find that each product will be A squared plus B squared, which is essentially magnitude squared of that vector X, which we know because there is distance, it is going to be greater than 0. Now, this will tell you that lambda equals lambda conjugate, right? If this and this are the same, then we know lambda equals lambda conjugate, which also implies that lambda is real. So if you have A as symmetric, right? So let me just, if you have A to be symmetric, then eigenvalues are real. All right, so that's the proof for that. So laid out in statement here. So lambda must be real. Let's move on here. So if you have a symmetric matrix, your eigenvalues are real, right? That's what we proved here. I'm going to show you guys how to evaluate eigenvectors and eigenvalues very quickly in MATLAB. So hopefully, if you have access to MATLAB, if you don't have access to MATLAB, I hope that you know where to get it from. All RPI students have a student license. You can download and install that from the .cio software for RPI. You should be able to get MATLAB. And to be able to access the eigenvalue or eigenvectors, right? This particular function here, EIG, to be able to use this, you don't need any special toolbox in MATLAB. The basic installation of MATLAB will get you this. So I'm just going to show you a few commands here, very simple, how to evaluate eigenvalues and eigenvectors for a given matrix. So the first example over here that I have is, you see, this is optional, right? Like the only reason why I'm showing this is because for those of you who have access to it and who want to sort of check your work, you can use this as your calculator essentially. So the first example that we have is for a symmetric matrix. And the moment you know it's a symmetric matrix, you know that it is real. It should give you real eigenvalues. So we are generating some random matrix here, right? Rand is uniformly distributed between 0 and 1 values, 5 rows and 5 columns. So when you look at A, it should be a 5 by 5 matrix in which each value is uniformly distributed between 0 and 1. Next, I'm taking that A and I want to get a symmetric matrix. A is not going to be symmetric matrix because it's randomly generated. But I can manipulate A in such a way that I get M, which is symmetric. So what I do is I take A and I take the transpose of A, add them up and take half of each value. And when I do this, I actually get a symmetric matrix in M. You see this? What I'm doing is I'm saying M, my new symmetric matrix, is half of A plus A transpose. And the reason why this is symmetric is because if you see what happens when you evaluate M transpose will be half of A transpose plus A, which is the same thing as M. So because M transpose equals M, you know that if I applied this, half of A plus A transpose, I would have generated a symmetric matrix in which all the elements were randomly distributed, right? Like uniform distribution between 0 and 1. So every time you run this in MATLAB, you will get a new set of values. But when I did it, I got these set of values. And you can see that these are symmetric. It's a 5 by 5 matrix M that I generated. So the first row is the same as the first column, second row is the same as the second column, third row is the same as third column, and so on. You can see that there is M transpose equals M. They're all real values. Now I'm going to use this one simple function in MATLAB, EIG, of that matrix M. So when I use this EIG function in MATLAB, it returns two things to me: all the eigenvectors and all the eigenvalues. All the eigenvalues go in D, all the eigenvectors go in V. Where are the vectors? These are the vectors. 1, 2, 3, 4, 5. I've got 5 eigenvectors and I've got 5 eigenvalues. The eigenvalues are all the diagonal elements over here. All of them are real. So I've got 5 real eigenvalues and 5 vectors, all real, corresponding to those 5 eigenvalues. Now, right, so this is pretty simple. Just a couple of commands. Enter any matrix, use the EIG function, and you will be able to see what the eigenvalues are going to be. They will be in D, and all the other elements are going to be, all eigenvectors are going to be in V. Next, I'm going to diagonalize this eigenvector, which essentially means I am taking these values in the diagonal and I'm diagonalizing it, meaning I'm making D diagonal will be just one vector here. So it'll have 5 rows and 1 column. The 5 rows will have these 5 elements. So I'm essentially taking these 5 elements and I'm arranging them in one vector. Then I'm going to see whether these are in fact eigenvalues and eigenvectors for this M. And the way I'm evaluating or checking is by evaluating this. Mx minus lambda x equals to 0 or not. And the way I'm checking is mv, right, m times the eigenvectors minus whatever diagonal I made here multiplied by x. So mx minus lambda x. And I will try to see what that residual is when I subtract them. And you can see that the residual has all these elements, obviously non-zero, but if you see this, everything is getting multiplied by 10 to the negative 15 over here. So for all practical purposes, this is a 0. Right? So there is a rounding error that is going on, which is why it is not giving you an exact 0. But you can see that it is 10 to the negative 15. So what that proves is these are the 5 eigenvalues real, for these 5 eigenvectors also real. Next, this was for symmetric matrix, right? So this was for symmetric matrix. Let me show you for any matrix. So here for the second case here, I'm generating a new matrix B here, which is randomly generated 5 by 5 square matrix. And it is not symmetric, just randomly generated. So I have no control over the eigenvalues and eigenvectors. And I'm using again EIG function here to generate all the eigenvalues and eigenvectors. And you can see that the values, actually, these are the eigenvalues for this randomly generated matrix, square matrix. You see, I got the first one is a real eigenvalue, the second one is a real eigenvalue, and the last one is a real eigenvalue. But the ones that are non-real, the complex eigenvalues appeared as complex conjugates, right? Complex conjugates there. Complex conjugate pairs. Of course, the other possibilities are all 5 could have been real, or the other possibility is you could have one real eigenvalue and 2 pairs of complex conjugate eigenvalues. Now, the same function EIG also gave me all the eigenvectors. So you see the eigenvector, there are 5 eigenvectors here. The eigenvector that corresponds to the real eigenvalue is real. You see a real eigenvector here, real eigenvector here, and the last one is also a real eigenvector here. However, the eigenvectors that corresponded to complex eigenvalues gave me complex eigenvectors. However, these are complex conjugates of each other. You see this value and this value, complex conjugate, complex conjugate, complex conjugate, and so on. So when you have complex eigenvalues, they appear in pairs, and the corresponding eigenvectors will also be in complex conjugate pairs. So this sort of checks that. All right, this is all I have for you guys for today. Our next class will be on factorizing matrices, and then later next week we have our exam. I'm going to set it up to be similar in terms of logistics to the exam that you did with Professor Stevenson, right? So there's going to be the automatically graded part on Gradescope, and no, it's not cumulative. No. So the exam here is only going to focus on matrix algebra. But I'm going to set it up in a way that was consistent with how exam 1 was set up. So free response questions and stuff that is getting automatically graded. So same kind of things that you did for exam 1, you're going to do that for exam 2. It is not cumulative. It is only on matrix algebra content. Other questions? Can we get more details on exam 2 later? Sure, I'm happy to give you more details. What kind of details are you interested in? So just let me know what kind of details. When is exam 2? So exam 2 is next week. It will have an automatically graded portion and a portion which gets graded. I think from what I remember, please correct me if I'm wrong, 20% of the exam was automatically graded, and then 80% was, will the questions be from the quizzes? Yeah, they will be handpicked from the quizzes. I may change some numbers, but they will be handpicked from the quizzes that you guys have already taken. The automatically graded portion. The rest of the 80% of your exam 2 will be based on free response questions, where you are actually going through, showing work, and then scanning your pages and uploading it to Gradescope. So similar to exam 1, right? Even in terms of everything, in terms of timing, in terms of length, as close to exam 1 as possible. But if there is anything else that you guys want to know, please let me know, and I can try to answer those queries. All right. I will see you guys on Tuesday of next week then. Can we see the correct quiz answers? Sure. I think if you guys can go and take a look, are you able to see the correct quiz answers or not? In any case, I will release the correct quiz answers as well, so you should be able to do that. But then the last quiz 10, is going to be released at 2 p.m. today. Except for that, all the previous quizzes, I will release the correct quiz answers. No problem. No problem, you guys. Is the exam going to be on a WebEx meeting? No. Exactly like exam 1. You guys remember exam 1 that you gave for this class? It was on Gradescope. It was not proctored. You guys remember that? You guys did it on Gradescope and you uploaded your work. It's going to be exactly like that. Oh, okay. You didn't take the first exam. All right. So what I'll do is this. I will try to post something on Piazza about how exam 1 is going to be conducted. So the logistics of exam 1 I'll post on Piazza. All right. Okay, you guys, stop recording here. Yeah, I need to stop recording here. And then, yeah. You guys have a good day as well.